Hello everybody, this is Tommy and welcome back to my weekly physics explainer video. Today we're going to be going over problem number 71 in chapter 21. We're only going to be doing part A of this problem, and it asks, a refrigerator using helium gas operates on the reverse cycle shown in the figure below. What is the refrigerator's coefficient of performance? That's going to be K equal to the heat that's taken from the inside of the refrigerator over the work that's put into the system. So the work that's put into the system is going to be equal to QH minus QC, where QH is going to be the heat that's dispersed into the surroundings after the heat has been absorbed from the inside of the refrigerator, and the heat that from the inside of the refrigerator that's getting put into the cooling solution is going to be QC. And this is the equation for both of them. Notice how I've labeled some of the points 1, 2, 3, 4 here, and we know that the point from 2 to 3, from point 2 to 3, it's going to be expelling some of the heat, so the temperature is going to decrease, and from point 1 to 4, it's going to be taking in the temperature. It's going to be taking in the heat from the inside of the refrigerator. From point 4 to 1, so that's going to be NCP over T1 minus T4. CP is just going to be a constant, which is going to be equivalent to 3 over 2 times R. In order to find both of these, we're going to need to know a couple of variables. So some of the missing variables are N, which is present in both solutions, and T3 and T2, which we're going to need to find QH. So first of all, we can start off by finding N by using the ideal gas equation. So we're given the pressure and the volume for the first point, and we know that we know the temperature too, since that's also given to us, and R is just a constant. So if we plug in all of these, we can get 0.00722 moles. And after we find that, we need to find T2. Oh, and by the way, some common pitfalls when doing the algebra on this is that the pressure is in kilopascals, so that's going to need to be converted to pascals, and the volume is going to be in centimeters cubed, so that's going to need to be converted to meters cubed. So we're going to find the temperature of the second point, which is going to be this point right here, and in order to find that, we can use the ideal gas equation, but since we don't exactly know the pressure, we can use the equation for an adiabatic process. So the pressure at point 2 multiplied by the volume at point 2 to the power of some constant, which is this constant's going to be dependent on the gas that we're using. So it's 1.67 for helium, since in the problem it states that we're going to be using helium gas to operate the cycle. And if we just rearrange this equation so that we can get the pressure of the first point multiplied by the volume of the first point to the constant over the volume of the second point to the constant power, then we can get 693,000 pascals. And then we plug it into the ideal gas equation and solve for T2, which is going to yield 462 kelvins. So after we find T2, we're going to need to find T3, which is going to be the temperature at point 3. We can use the same trick, which is just using the adiabatic equation, except instead of going from point 1 to point 2, we're going to be going from point 3 to point 4 instead. So after doing that, we can try to solve for it, but then we realize that we're going to need the pressure at point 4, because if you notice above, at point 4 we're given the volume and the temperature but not the pressure. So we can just use the ideal gas equation in order to find the pressure at point 4. So after using the ideal gas equation, we're going to get 120,000 pascals, and then we're going to plug that into the adiabatic equation, and we're going to get 554,000 pascals. So after we solve for the pressure of the third point, we can now use the ideal gas equation to find the pressure of, in order to find, not the pressure, the temperature of the third point, and that's going to give us 369.2 kelvins. So now that we have T2, T3, and N, we can now use both of these equations and solve for QH and QC. So we're going to plug in the number of moles, plug in this constant, and plug in the temperatures. And when we do that, we get QH is going to be equal to, notice that there's an absolute value around this equation. So even if it's negative, it's going to be positive, of course. So that it's going to end up being 8.39 joules for QH, and for QC it's going to be 4.51 joules. As we know from earlier, the work in is going to be QH minus QC, so that's going to be 3.88 joules. And finally, for the coefficient of performance, we're going to need to put QC over the work that was put in, and that's going to be 4.51 over 3.88, and that's going to yield 1.16, and that's going to be our coefficient of performance. Thank you.